Welcome back to Code Meets World, and today, after completing the 2 easy problems in the heap priority queue section, we are moving on not to graphs because there aren't any easy ones, but to dynamic programming and the climbing stairs problem. So in this one, we have some very simple instructions that you are given, you're climbing a staircase and it takes n steps to reach the top. Each time you can climb 1 or 2 steps. So we want to know how many distinct ways there are to climb to the top. And we have some examples where if n is 2, this makes sense, the answer is 2 because there's 2 possible ways to get to the top. You take 1 step twice or you take 2 steps once. If we try to have the top of the stairs be 3 steps away, there are 3 possible ways you can get there. 1 step each time, 1 plus 2, or 2 plus 1. And n can go up to 45. So for instance, if there were 45 steps, we would need to figure out how many possible ways you could reach the top by going either 1 or 2 each time. So let's jump down to the whiteboard and talk about how on earth we're going to solve this. I have a few ideas, but I'm not sure where the dynamic programming comes in, actually. So whenever I see a problem like this, I instantly think recursion. And I know we did that in an earlier section, but that's what I think of. So let's talk about how we might be able to do this. Say that n equals 10. What we essentially want to know is how many possible ways are there to get to the 10th step using only 1 or 2 step increments. And what that actually means is we need to know, well, how many steps does it take to go to 9 steps? How many steps does it take to go to 8 steps? Because my theory here is if we know how many steps, how many different ways you could get to the 9th step, and we know how many different ways you could get to the 8th step, because you can go from the 9th step to the 10th step, or from the 8th to the 10th. We just need to add these 2 values together, and that gives us our answer. So basically, I think step 10 equals step 8 plus step 9. And what I mean is the number of steps it takes to get the number of different ways you can get to the 10th step is equal to the number of different ways you can get to the 8th step plus the number of different ways you can get to the 9th step. Another way to write this would be more generally, for whatever step n we're trying to get to, this is the same thing as step n minus 2 plus step n minus 1. And this instantly feels recursive, right? Because you might ask, okay, well then how do we ever figure this out? Well, the base case, as we say in recursion, we're given that. You can get there with 1 or 2 steps. And we know exactly how many steps it takes to get to those. So what I mean is, we know that step 1, so how many different ways can you get to 1 step? That equals 1. And step 2, how many different ways can you get to step 2? There's 2, because you either take both steps at once or 1 and 1, just like it shows here. So I see how we can do this recursively. So I think I'm going to try, because I think this will be a very simple solution. So I'm going to try to write this code first, and then we're going to think about how we use dynamic programming. Okay, so let's write this code that I just described on the whiteboard and see if this is a valid solution or what we might be missing. So thinking back to when we did all the recursion problems with the trees, I think what I'm going to do is define a recursive function And I'm just going to call this solve. Maybe I'll change the name in a moment. But solve is going to take in just n. And what it's going to do is, first the base cases. If n is 1, we're going to return 1. Right? Because if we only have one step to go, there's only one possible way to take one step. However, if n is 2, we should return 2, because again, if n is 2, we have this one. There are 2 possible ways to get to 2 steps. I suppose I could also add 3, but I don't really need to, because I think once we define those 2 base cases, everything else can be calculated. If neither of these are true, we can simply say return solve of n-1 plus solve n-2, like that, right? Because if it's greater, say it's 3. If this is 3, none of these happen. So instead we return solve of 3 minus 1, which is 2. So solve of 2 plus solve of 1. Well, solve of 2 is 2, solve of 1 is 1, so those get added together to be 3, and as we can see here, that's going to work. And it should just do the same thing for all the bigger values as well. So then we can just say return solve of n. And we can run this. Okay, great. So that works as expected. Let's give it, because this is just testing those, let's give it a bigger value. Let's give it, for example, 6, and see if that works. Because if this works, I have confidence that this is a valid solution. And yeah, that does work. So maybe you don't need dynamic programming to solve this problem. Unless I time out, which would actually be super interesting. Yeah, look at that. For 44, and the max that we can have is 45. It actually times out. It looks like it times out for a lot of them, actually. So that's super interesting. Let's jump back down to the whiteboard and think, I have an idea of why this might be happening. So let's talk about that. Okay, back to the whiteboard here. And we just timed out with this solution. And thinking about it, I have an idea why that might be. And I think it has to do with repeated values. So let's talk about n equals 10 again, if we're given that. In the algorithm that I just wrote, what we have to do is calculate the n-1 case plus the n-2 case, right? So in the n-1 case, I have to run the algorithm on 9. I also have to run it on 8. This is a recursive algorithm, so cool, that makes sense. But then to solve it for 9, I have to run it on 8 and 7. Over here, I have to run it on 7 and 6. Can you see where we already have a problem? To solve this side of it, of the recursion, I have to find, actually let's put this in a color. I have to find the value for 8, but look, I have to find the value for 8 over here, and this is the entire side of this tree. And again, the 7s are repeated. If I keep writing this, I think we see what happens. This turns into 7 and 6, this turns into 6 and 5, this one is 6 and 5 as well, this one is 5 and 4. But look at all these repeated values. 7 again, so there's 3 7s. There's 1, 2, 3, 4 6s. 2 5s. Basically, everything is going to be repeated. There's 3 5s. We're doing all of our calculations more than once, and many times, tons of times. And so that's probably slowing us way down. So what I think we can do instead, and of course this is a dynamic programming problem, so I should have guessed it would be something like this. Instead of calculating the recursion of both sides at the same time, what we could do is only do one side, the bigger side, and every time we calculate something, we'll store it in a dictionary. So for instance, once we go through and recursively find what the value is for 8, what it is for 7, what it is for 6, once the recursion executes, we can just save those values. So maybe 6 takes 50 steps, and maybe 7 takes 110 steps. These are just guesses. But once we have all of those from the first cycle, when we go through and calculate the second one, so that we can do this part of the calculation, we have access to all of these values already, and then we just instantly calculate them without ever having to do it twice. I think this might be the way that we can do it. So let's jump back to the code now, and let's see if we can update to use this solution. Okay, so back on the code, what we've basically decided is we have to change this solution so that we have a dictionary of some sort. So what we could say maybe is dict equals just an empty dictionary. And then instead of returning this, what we can say is dict n equals that, and then we return dict n. Sorry, can't spell. Dict n like that. So far all I've changed is, instead of returning this value, we're just going to save it in the dictionary before we return it. So really the code hasn't changed at all. We're just saving the value so that we can use it again. And I think how we would use it again is simply saying, before we check even, so we've only been checking the base cases of 1 and 2, but now we can check anything. Because if we've seen any value before, at any point during our recursion, we should have the answer saved in the dictionary. So I should just be able to say if n is in the dictionary, if that is true, then we can just return whatever is in the dictionary at n. Sorry for the crazy looking formatting here. I don't know, there's some sort of bug with LeetCode when you edit code. Like, these shouldn't be different colors, but anyway. So all we've changed here is we're saving the value each time, and now we're checking if we've seen this, if we've calculated this before. Let's just return that instead of recalculating it. Let's see if this works. Okay, great. So it still works. I'm not sure if this is faster or not, but hopefully it is. Yes, perfect. Amazing. So yeah, that's a quick solution. Did pretty well, better than 70%. The storage isn't that good, and I think that's because I'm saving every value in the dictionary when I probably don't need to do that. For instance, I could work from the top down, and once I've used 9, 8, 7, I could probably remove them or something like that. But I'm overall very happy with this, and yeah, I hope this was helpful. Thanks so much. See you in the next video.